In elementary calculus, we take it for granted that we can always zoom in on a point. But as we move into abstract spaces, we need a formal way to describe how points are grouped together. It begins by asking a specific question. Does a set of points have a boundary, or does every point have room to breathe? To answer that, we rely on the most basic tool in a metric space, distance. By picking a center point, x0, and measuring out to a fixed radius r, we define what mathematicians call a ball. We classify these balls based on their edges. If the ball includes only the points with a distance strictly less than r, it is an open ball. If we include the points where the distance is exactly equal to r, we have a closed ball. This gives us a rigorous way to define a neighborhood. If a set completely contains an open ball around x0, it is a neighborhood of that point. It means that even if you move a tiny distance in any direction, you are still safely inside the set. However, we have to be careful with visual intuition. In a discrete metric space, the distance between any two different points is exactly 1. If you draw an open ball with a radius of 1/2, the only point inside that ball is the center. There is nothing else there. Because distance can behave so strangely in these abstract settings, we have to anchor our definitions of open and closed in metric axioms, rather than what we see on a 2D plane. We use these balls to categorize the points within any set. If we can fit an open ball around a point x so that the entire ball stays inside set M, then x is an interior point. But if a point y sits exactly on the edge, it's different. Any open ball around y, no matter how small, will contain some points inside M and some points outside M. This is a boundary point. This leads us to a formal definition. A set is open if every single one of its points is an interior point. In other words, an open set contains no boundary points. A closed set is defined by its relationship to the space around it. We call a set closed if its complement, everything outside of it, is an open set. It's a common mistake to think that if a set isn't open, it must be closed. But sets aren't like doors. They can be both open and closed, like the entire space itself. Or they can be neither, like an interval that includes one endpoint but not the other. Treating open and closed as independent characteristics is the first step toward understanding the structure of more complex topological spaces. Open sets follow a strict set of operational rules. You can combine any number of open sets into a union, and the result is always open. But for intersections, the rule only holds if you are overlapping a finite number of sets. If you take an infinite intersection of open sets, like a series of shrinking open circles, they can eventually collapse into a single solid point. That point is a closed set, which breaks the open set rule. These rules allow us to do something remarkable. We can redefine the concept of continuity without using any numerical measurements at all. Under Theorem 1.3-4, a mapping is continuous if the inverse image of every open set in the target space is also an open set in the starting space. This topological definition means we can analyze continuous mappings in spaces where a standard ruler or a numerical delta might not even exist. Beyond classifying sets, let's look at how points cluster. If every neighborhood around a point contains another member of the set, it's an accumulation point. Add all accumulation points to a set, and you get its closure, the smallest closed set containing your original points. Sometimes a subset is so well distributed, its closure becomes the entire space. This is a dense set, like rational numbers, scattered so thoroughly they approximate any real number. If a space contains a countable dense set, it's separable. Not all spaces are this manageable. In the space of all bounded sequences, there are uncountably many disconnected sequences that sit far apart. There is no countable list that can approximate every point here, making it non-separable. To summarize, open sets provide breathing room for every point. Closed sets are the complements of open sets. The closure seals a set with its accumulation points, and separability tells us if a space can be approximated by a countable list. These definitions are what allow us to map, measure, and approximate behavior in any mathematical space. If this overview helped you understand the topology of metric spaces, Like the video, subscribe, and let us know in the comments which chapter of functional analysis we should tackle.